Hello, am I audible? Am I audible?
Yes, sir. Yes, sir.
I think only you have joined. Let us wait for 2 minutes if someone else also join.
Okay, sir. Okay, sir. Okay, sir.
Okay, I think it is already 2 minutes over. We can start today. Can you see my screen? Just a second. Yeah, can you see the screen?
Yes, sir.
Okay, so let us start. So we'll start from the part we left last class. So what we studied? We studied the basic things about magnetism, then magnetic materials, paramagnetic, uh, ferro or antiferromagnetic, okay, these things. So we'll start with the link from that part. Okay, so we already know about this term that is called spin orbit coupling. Okay, where you have some orbital momentum contribution to the observed magnetic moment. Okay, so one is your magnetic moment spin only, and there will be a difference between the observed magnetic moment. Okay, so this can come from either spin orbit coupling. This you can also designate as orbital contribution, and another one will be contribution from low lying excited state. What is that? I will come into it. Okay, this we have already studied a bit about spin orbit coupling. Just a second. Okay, this we have already studied a bit, so we'll continue with that. Say, you know, what is the orbital contribution? Orbital contribution. So you have a electron configuration like this. This is your EG set. This is T2G. So this all will be same spin direction according to Hund's rule. And then one electron will come in one of the T2G set orbitals. Now this electron can come either here, it can come either here or here or here, right? And what we know of T2G set? T2G set consists of dxy, dyz, and dxz. But these are different, right? The shape of these orbitals or the direction of these orbitals are different. So let's say we will have this axis x, z, and let's say this is y. So this will be your dxy in between axis. Okay, uh, just a second. So this will be your dxy, and what will be dyz in between this one will be dyz, and and dzx will be somewhere like this, okay, in between z and x. So if electrons are placed in one of those orbitals, their effect will be different. Okay, so that's why their contribution is also different. And from here, this orbital contribution come. So you need to remember, when this orbital contribution will come, this will come when there is some asymmetric electron filling in either T2G or EG set. Okay, let's say an example. For example, cobalt 2 plus. Cobalt 2 plus is D7 system. So D7 system will be like, so first you feel like this. So D7, this is high spin. 1, 2, 3, 4, 5, 6, and 7. Now you have one unpaired electron. So this is asymmetrically filled. Asymmetrically filled. You can have different configuration. You can have one like this. So this will be single always. So your single electron can stay here. Sorry. Okay, or it can stay like this, or it can stay like this. So suppose this is your dxy, this is dyz, this is your dxz. So as the electron will be staying at different orbitals, the contribution from it will vary to the magnetic moment. Okay, this is called the orbital contribution, and that is why you will get the observed magnetic moment higher than the calculated. Okay, this is one thing. Another thing is that contribution from low lying excited states. What is low lying excited state? What is low lying excited state? This also will explain with the same example with cobalt 2 plus, okay, high spin state. So suppose you have like this. This is your T7 system. Now you promote one electron from here. So let's say you promote this electron to here. It will be like, okay. Now you can see all the sets are asymmetrically filled. Okay, so from ground state also you are having some, this orbital contribution. From excited state also you are having some orbital contribution. So that is why your magnetic moment can be, you know more than your expected value. So whenever you are trying to explain some questions, the question will come like this. So they will give some magnetic moment value that will be you know, some anomalous. Okay, anomalous value that will be not expected. So you have to explain what is the reason. Okay, so if it is just a little bit of excess, little excess moment, then you can check electron configuration. Okay, if there is possibility of orbital contribution, okay, that will be your answer. But if there is you know no possibility of orbital contribution also, that time you can refer to, if not then refer to low lying excited states. Okay, so now with that we complete this part of 3D metals. Now we are going to magnetic properties of lanthanides. So lanthanides, most common oxidation state for lanthanide is lanthanide 3. Okay, lanthanide 3. And you know that all lanthanides contain inert F electrons. Okay, due to these F electrons only they are called lanthanides. Okay, also actinides also, but if you think of magnetic properties, actinides are not that much important. So main focus is given on the lanthanides. Okay, so actinides and lanthanides. So now let us see that where are the F electrons present. So basically they are present in n minus 2 shell. Okay, so it will be like 6s2, then 5d something 0 1 or something like that, and then you have 4f, then you have 1 to 14. It will be like that, the electron configuration. So this is of most importance. This will be n minus 2 level. So n minus 2 level, that depicts or it indicates that it is inner, inner or core shell. That means it is not exposed to ligands, right? So what we saw for 3D case, for 3D cases, what we saw that your metal orbital d, okay, this is directly interacting with the ligand. hmm? So your 3D, this is your d orbitals. Okay, so they are directly, ligand can affect them. They can send, they can give electrons or they can take back electrons also. This is sigma, this is pi. So they can give sigma donation also, and they can take by pi bonds also. So that is why d block elements or d orbital especially is much more uh, affected by the ligand field, but not for the F case. So F if electrons are not, there's a special term we use that is called perturbation. Hmm. Those you have studied quantum mechanics, I think. So maybe you are familiar with the term that is called perturbation. So that is called the effect of external factors into your, intrinsic system. So if electrons are not perturbed by external ligand field, what is the effect? What is the effect that it does not get affected by the ligand field? So you can see, say any spectra is UV spectra. UV spectra, X you have lambda, that is in nanometer wavelength, and here you have absorption intensity. Hmm. So in any complex you measure, what you will observe, you have a band for, say, your ligand, that is pi to pi star. This will be pi to pi star, and then you have metal centered band like that. So this will be some charge transfer band, charge transfer bands, maybe metal to ligand, metal to ligand, or ligand to metal, depend on your metal center and the ligand you choose. Okay, the interesting thing, or the thing that is we will focus on, is that the broadness, broadness of spectra. Why? Because all these bands which is coming from the metal electrons, which is a property of the metal, they are all overlapped. Okay, because there is effect of the ligand field. Broadness of spectra, this is the effect of ligand field overlap, whatever you say. Hmm. But as for lanthanides, we don't have. Just a second. This is for 3D gas. But for lanthanides, you don't have such things. Your F electrons are not affected by the ligand. So there, what you will observe, to do the same thing, your metal centered spectra. So ligand will be same, okay, but metal will be very sharp. Sorry. Uh, this is ligand. This will be your metal centered spectra. We'll get to see something like this. So these things will be very sharp, okay, for F electrons. Okay. Why? Because there is no ligand field effect. Okay. Is it clear?
Yes, sir. Yes, sir.
Okay, sorry. Um, so with that, what are the points we know? Ligand field effect is pure. Ligand field poor, and their magnetic properties independent of ligand field. Then, so as they are independent from ligand field, so here what you can see, uh, spin orbit coupling orbit coupling T dominates. Okay, spin orbit coupling T dominates. So uh, there is a fundamental difference. So in case of D, in case of 3D, say the splitting you see T2G and EG, these are based on based on ligand overlap, because you have, you have some orbitals do not interact same way with ligands. Why? Because you have T2G along, sorry, T2G in between axis, and you have EG along the axis. So that is how we give much more uh, attention to ligand field splitting. Sorry. But for lanthanide case, ligand field effect is not there. She will only have effect of spin orbit coupling, and this coupling is in termed as many other terms. So some people call as RS coupling. Okay, then spin orbit coupling you can use it, and okay, let us get into it. So suppose you have two terms. One is called orbital angular momentum, that is depicted by capital L, and then have spin angular momentum, that is called capital S, and then you have resultant total angular momentum, that is called J. Okay, and how? So there is one more term that arises in a block, that is called microstates. Okay, it's a property of what can I say, property of certain electron configuration. So there is one term that I am forgetting right now. So microstate is like a uh, quantum state. So this will be the minimum. Okay, you cannot go beyond that. So for a given electron configuration, for a given electron configuration, such as, say, we are considering D2 system. Okay, D2 system can have total number of microstates. There is a formula, is n factorial by r factorial n minus r factorial. Okay, where where n is total number of electrons. uh, so total, not total, appropriate term will be maximum. Maximum number of electrons can be accommodated. R will be available number of electrons. Okay, so if you calculate this one for D2 systems, what will it come? So for D2 is d orbitals. So d orbitals can have maximum of 10 electrons. Electrons maximum. If you have any doubt at any point, you can stop me and ask. So then this formula becomes 10 factorial by, so in D2 you have 2 electron, 2 factorial, 10 minus 2 factorial. So what it comes? So this is 10 factorial by 2 factorial into 8 factorial. So this you can write as 10 is into 9 into 8 factorial by 2 factorial into 8 factorial. So this can go, this can cancel off, and then you have 90, 2 factorial is 2, that will be 45. Okay, this is the total number of microstates. Okay, and these microstates, each of the microstates are uh, represented by two notation. One is called term, one is called term symbol. Okay, so it is written like this: 2s plus 1 L, and term symbol 2s plus 1 L, then J. The J value can be L plus S to L minus S with one gap, like L plus S, then you can have L plus S minus 1, then L plus S minus 2, so on. You can go to L minus S. Okay, each of the microstates are presented like this. So let us move forward. So as I told you, so how you will calculate? So your observed magnetic moment is, is just not only your spin only value. Okay, it has some orbital contribution here. So how we will calculate that? The formula is nu j equal to gj. Okay, I will tell you, this is called a Lambda g factor. This is j into j plus 1, and this is Bohr magneton. This is called gj is Lambda g factor. So it is not that gyromagnetic ratio. You should remember it. This is a separate term. And J, J is the LS combination. And then how do you calculate G? The formula for calculating Gj is like this. So many people write it a different way, but I prefer to like it that way. 3j, j plus 1 plus s into s plus 1, then l plus 1, and on the denominator you have 2j, j plus 1. This is how you calculate. So then you have certain cases where your j can be L minus s for ground state, and for some cases j will be L plus s for ground state. So this is generally applied for L minus s is applied for uh, f0 to f7, that is less than half filled, and this is for f8 to f14, more than half filled cases. How does it come? I will come into that. Now if you have f7 and f14 in these two cases, then your L will be 0. Okay, so before that I have to show you how this L is calculated. Let's say calculation of L. So let me show you by determining one ground state of a certain configuration. That will be great. So let me find one example. Yeah, let us take an example of very easy, uh, that is p. Okay, p orbital. So I will take carbon configuration is the configuration of the uh, you know um, previous noble gas helium. Then you have 2s2 and 2p2. So we are concerned about this one. So p, you have three orbitals, px, py, and pz, right? So now let us first calculate the number of microstates. Number of microstates will be, as I told you, n factorial by r factorial n minus r factorial. So p can hold maximum 6. Hmm. Then you have 2, 2 factorial, 6 minus 2 means 4, 4 factorial. So here you will have 6 into 5 by 2, and then it will be 15. Okay, 6 and 2, 4, 5 and 2. Okay, it's fine. So most common microstates are 1d2, 1s0, 3p2, 3p1, and then 3p0. As I told you, this term, this top term is 2s plus 1, middle term is L, and this term is J. So S is called in S is called number of spin. Hmm. Let's say I am considering this one. my 2 electron is in px orbital. Okay, now number of spin he says, let me finish this one. L is your total number of ml values, and azimuthal quantum number j is, so you can see it is less than half filled. So for p it is less than half filled, so it should be minus l minus s. So let us first consider this one. So ml values are like this. So plus 1 0 minus 1. Okay, if you had for some case d will be like this, 1 2 3 1 2 3 4 5. So it will be plus 2 plus 1 0 minus 1 minus 2. Okay, I will come into one example of d. Let me finish with p, then I will come to d. So now see, number of, so one more thing.
Hello,
Yes,
sir. Px in px orbital, number of electrons is 2, 1, 1. Px and py.
sorry.
P2 है ना? Number of.
Yeah, this is p2. No, I will show you what is the difference. So ground state I will calculate.
Okay, okay.
But I will show you the differences. Okay, how they come.
ठीक. Okay, sir.
So for this case, suppose this is in one orbital px only, it is residing. Huh? Then what will be the term symbol? So you can see here your ml value is plus 1. You have 2 electrons. That total l value will be 2, right? 2 electrons you have. You have plus 1 ml value here. So l will be 2, and so here s is number of unpaired spin actually. Okay, unpaired spin. So here you don't have any unpaired spin, all are paired. So S is 0. Okay. Then what is this 2s plus 1? This we called 2s plus 1 is spin multiplicity. Multiplicity. Okay. So 2s plus 1 will come 2 into 0 plus 1, that is 1. Okay. And for L we have a notation for L. Just like you have, for azimuthal quantum numbers, you have L 0 1 2 3 4 like that. So what you have S P D F, like that. You have the orbital numbers, right? So here also you can do the same for terms for L. So let me see, write like that: 0 1 2 3 4 5. So for this one capital will come, so capital S P D F G H and so on and so forth. Okay, so now you can see your L value is 2. So what is this term symbol of this particular configuration? So you have to write the spin multiplicity, that is 1. So you have 2, that is D, and then you have L minus S because it is less than half filled. So your L value is 2 minus S is 0. This will be your term symbol of this particular state. But why it is not the ground state? So for ground state you need to consider something, some rules. Let me wipe up this part. For ground state determination, for ground state there are actually three rules that you should consider. First rule is the spin multiplicity, that is 2s plus 1, it should be maximum. Okay, why? Because say I am taking two configuration, px px py and pz. Here also I am taking another configuration, same px, py, pz. As I told you, this is 1d2, okay, microstep. So here you have two electron, same orbital. So for that you have strong repulsion. Strong repulsion leads to high energy. Let me put these electrons in some other orbitals. So now you have two electrons in different orbitals, then repulsion is less energy. Okay, that is how you prove your first point, that spin multiplicity should be max. So for this one your spin multiplicity is 0. For this one you have two number of spin, then your s will be 2 into half, that is 1. 2s plus 1 will be how much? 2 into 1 plus 1, so that will be 3. Okay, so for higher spin multiplicity your energy is less, so that will go to the ground state. And then when you fix your first point spin multiplicity for same spin multiplicity, your just a second, your L value should be maximum. Okay, and the third rule, as I told you, that is for less than half field, ground field J will be L minus S. For more than half field, ground state J will be L plus S. So these are the three rules that you should consider. So these are the rules coming from Hund. Okay, from Hund, the consequence of Hund's rule to determine the ground state of the uh, of different microstates. So in our case, let us consider this one. So this is clearly not the ground state, as it is having less, you know, spin multiplicity. We can see we have other states that are having, a higher spin multiplicity, so this cannot be the ground state. So let us consider other case, this one. Okay, let us calculate for this one how much. Let us calculate the term symbol here. So what is your L value? Just a second. So L value will be, so if this is plus 1, 0, minus 1, so if this is plus 1, 0, minus 1, L will be 1. Okay, L1 means it will be P. Then you have spin multiplicity 2s plus 1 equal to, so you have two half spin, so spin will be 1, and 2 into 1 plus 1 is 3, right? And then 3 P, J will be how much? So L minus S, so 1 minus 1, that is 0. So this will be your ground state. Sorry, this will be your ground state, right? Now you can ask me that why we are putting the electrons in px and py only. We can put in px and pz, right? Okay, or py or pz. So if you do that one other scenario, if you do it like this way, px, py, pz. Now check your L value. Okay, this is 1 minus 0. So in this case, your L will be 0, right? So as I told you, L should be maximum. So that is how we determine the ground state. Okay, so where we was we were okay for the F electrons. So did you understand this concept?
Yes, sir. Yes, sir.
Hmm. So for F electrons, if your configuration is F7 or F14, so let me just, sorry, it will be F14. Let me just draw it, the shells. 1, 2, 3, 4, 5, 6, 7. Okay. Now you can fill it like this way for the ground state. This is F7, and it will be 0 plus 1 minus 1 plus 2 plus 3 minus 2 minus 3. So here your L value will be 0, right? And then if your L value is 0, when you calculate this Gj, 3 J plus 1 plus S into S plus 1 minus L into L plus 1 by 2J, J plus 1. So what was J? J was L plus L, sorry, L plus S, right? So now L is 0, then J will be S. Okay. So then all these terms will get cancelled. You will get G value equal to 2. Okay. And now you calculate this new J, it will come similar to your spin only value. This is the case, okay, for F7 or F14 systems. And I already told you the difference between term and term symbol. So whenever you are going to the J term, so I have written, just a second. Yeah. So term means only you are considering spin multiplicity and overall your L value. But when you are going to the microstates, considering the J value also, that will be your term symbol. So this is some silly things that should people should take care of while answering questions also. So with that, let us move forward. Yeah, and that thing I told you, that effect of low lying excited state. So generally, what we calculate the magnetic moment for different ions will get in vicinity of that observed moment. But for some ions like uh, europium 3 or samarium 3, like that, will not get expected magnetic moment and observed magnetic moment different. Okay, this is for this contribution from the low lying excited states. Okay, so europium, let's see for the example. Europium 3 is actually 486. Okay, and its term symbol, ground state term symbol is 780. Okay, so if you calculate the magnetic moment, you will get 0. Okay, you can try out yourselves. If you calculate this one from this term symbol, you take L, S and everything value. So here 2s plus 1 is 7, then your 2s is 6, s equal to 3. Okay, and then uh, if f means L is what, uh, so SPDF, so L is 3. okay, and J is 0, right? So S and L, they are same. So you can calculate this magnetic moment and it will come 0, but experimentally mentally you get around 3.5 more magneton. So this is the contribution from the low lying excited states. So this is much more uh, pronounced for the lanthanides, much more pronounced for lanthanides. Okay, basically the core of the basic idea is that lanthanide magnetic properties are the property of their metal center inherent. These are not coming from the ligand overlap. Okay, this is the difference between lanthanide and 3D transition metals. After that, uh, something that is already been discussed, like nature of magnetic materials, para, ferro, antiferro. So these are all have been discussed already. So I will just give some light onto some particular topic. So suppose you have this card. So when you do some magnetic measurement, we always check the sample. So suppose this is M and this is H. H is called, okay, magnetic field. Magnetic field. Sometimes also it is denoted by B. Okay, external magnetic field. M is called magnetization. Magnetization. Magnetization means how much, how much your material is magnetized, or it will be better if I uh, term it as induced magnetic field. Okay, induced magnetic field. So this is the property of material. Property of material. Sorry. Okay. So you can have different type of responses in different type of solids. If you have this kind of response, a straight line like this actually comes from paramagnetism. Okay, but if your response to the magnetic field is not linear, it is a linear response, a straight line. But if your signal is like this somewhere, say it is like this is called ferromagnetic behavior. Okay, so so the point at which this magnetization becomes constant, this is called this point is called saturation point. Now in modern day magnetometers, we can provide field both in positive direction and negative direction. Okay, this is your magnetization axis. So you can have positive field, you have negative field. Okay, magnetization also can be positive or negative. Now you have two different scenarios. So let me first draw it and then I will tell you. Okay, so this is a typical magnetization curve for a ferromagnetic substance. For ferromagnetic substance. If it was paramagnetic, then the response would be linear, not like non-linear. Okay. Then you have certain things to notice. This non-linear response. One is called saturation magnetization. Okay. So two things are there. So when this is called actually, this width is called hysteresis. Hysteresis is nothing but a memory effect. So I think you guys are already well aware of this effect. So if you have some iron ore, okay, that is very much magnet can be magnetized. Okay, so if you magnetize it with some other a permanent magnet, when you remove that magnet, so for some time it can retain its magnetic property. So it can behave as a magnet for some time, right? So this is called a ferromagnetic substance. So when you remove your external magnetic field, after removing also your substance or material can behave as a magnet, induced magnet, right? So this is the thing when you explain in Karpov graph. So uh, suppose I am increasing the magnetic field, external magnetic field, and that sample is getting magnetized. My moment is getting increased. But when I remove it or when I decrease it, it is not following the same path, right? It is not following the same path while decreasing. Okay. So there is some remnant magnetization that is present inside the sample that I cannot demagnetize. This is the nature of ferromagnetic substance. And where you can see this hysteresis, where you can see hysteresis with, okay, hysteresis with this one is large, that is called hard magnet. Uh, all classical magnets behave like this. Okay. If your hysteresis with is small, then that is termed as soft magnet. All the chips we use inside our electrical circuits, okay, they are kind of soft magnets. Okay, so electronics parts. So two more points are there. So at zero magnetization, so at a certain field where zero magnetization is there, it is called coercive field. Coercive field. And at zero field you have some remnant magnetization present. This is called uh, actually remnant magnetization. So all these things are important when you are classifying an ferromagnet. Hmm. How much is your remnant magnetization after you apply the field? Okay, at zero magnetization, what is the coercive field of that material, and altogether the hysteresis width of the material. Okay, so this is small, this is large. That is how we differentiate the ferromagnetic property of a material. Hmm. Then you have magnetic coupling between metal centers. Look, all of the systems that we consider, let's say we are considering one metal complex like this. You have all six ligands, this is octahedral field. Okay, and in solid or solution, so different unit will stay like this. So in a material, you will have different molecules, different number of molecules. In a unit cell, maybe you have two number of your molecule or three number of molecule. They are dispersed. Always they are dispersed in the system. Okay, but think of some case. Think of some case where your metal is either directly bonded or your metal is breached via bridging ligand. This is called a bridging ligand. Bridging ligand. This can be oxygen, nitrogen, cyanide, like that. Okay. Sulfur also can bridge. So when two metals are uh, are coupled like this through a bridging ligand or by a bond, this is called magnetically concentrated. Magnetically concentrated. But when your metal centers are far apart, okay, they don't have common linkage, okay, or like a covalent bonding, something like that. They have no direct interaction between them. These are called magnetically dilute system. So here the communication communication in between two metal center is less. Okay, or we can say coupling is less. But here in these two cases, coupling is more. Did you get it? Did you understand up to this?
Yes, sir.
So this coupling, just a second. This coupling, this can be either ferromagnetic or can be antiferromagnetic. Okay, suppose you have two metal centers. So you have one metal, this metal orbital, this is one metal orbital. You have one unpaired electron, you have one unpaired electron. Okay. Now, if you don't have anything in between, like they are dispersed, as I told, magnetically dilute system, they are dispersed here. So if you measure the magnetic property, it will give you a paramagnetic behavior. It will show as paramagnetic. But same case, if you have some ligand out there, so let's say you have a ligand here, bridging ligand, but it has the electrons. Okay, it's a paired electrons it has. But what will happen? There is a effect. It will have polarization. It will have polarization such that there is some spin flipping happening in the metal centers. So ultimately, it will be like L. This is also M. So suppose your electron is this way, then other one will be like that. Okay, then it will be like this, and then it will be like. Now you see how these are pairing up. These are opposite spin. Okay, these are pairing up, right? So if they pairs up, then it will be like two coupled spin. So there is no unpaired electron, and it will behave like diamagnetic. So this coupling is called antiferromagnetic. Okay, and if you measure the magnetic property, if you measure magnetic property, say this is your moment, this is your p. So suppose you have a certain moment up to some temperature, that is 100 Kelvin or 50 Kelvin, and after some point you will have a sudden decrease. You will have a sudden decrease like this. It will not go to zero, but it will have some magnetization left. So this kind of phenomena is due to antiferromagnetic interaction. And similarly, if you observe some other effect like this, the magnetic moment here, here is a field, and then your moment is like that, and after some point it is increasing like anything. Okay. So when it is increasing, this is due to ferromagnetic interaction. That is after some certain point. Okay, after some certain temperature, that is called critical temperature. Also, this, Coody and Neal temperature for ferro and antiferromagnetic interactions, right? So this is okay, and with that, okay, magnetism part is complete. Then the last part of this also, actually there is a lot of things are left in coordination chemistry, but fine, because it is you know uh, a touch up to the different aspects of inorganic chemistry, so we don't have much time to discuss all of the things. Otherwise, from this spectroscopic term, we could have gone to advanced spectroscopy, that is considering your term symbols and different transitions. Okay, so you have heard about like Orgel diagrams, Tanave-Sugano diagrams, right? So these are the main interesting part of coordination chemistry when you are going to study the advanced spectroscopic analysis. But this is not part of this course. You will study somewhere when you will have some particular course on coordination chemistry, right? There we will study the advanced topics. So with that, we move to the last part, that is bio inorganic chemistry. So metals are inevitable in biological systems, right? Okay, starting from chlorophyll to our hemoglobin. Okay, so metalloproteins helps to function all the organ properly. Then metal containing drugs and pharmaceuticals, uh, life-saving medicines. Okay, you already heard about this cisplatines and similar things. Okay, now uh, things things of concern is, so you can use the metals that are used as drugs and specific, you know, specific task are not redox active. Okay, like zinc. Okay, like magnesium, like that. Because redox active metal ions cannot do a specific type, cannot sustain, uh, variety of conditions. You change the pH, okay, you change your oxygen pressure, you change some other parameters, this will not be stable, okay, because the reduction potential is so less, or you can achieve this so easily that it will get oxidized or reduced, so they will not uh, you know maintain the stable form. So that is why for specific tasks we don't use this kind of metal ions that are redox active. So what are most used redox active metals? That is iron and copper. So iron can juggle between iron 2 and iron 3. This is a redox couple, and copper can also be between copper 1 and copper 2. So iron, so iron, it is present in our hemoglobin and myoglobin. Okay, then it is also used, for oxygen transfer also, and some other proteins. Then copper you have in hemocyanin, okay, and blue copper proteins, okay. And what else? Yeah, if you categorize metal ions in terms of abundance in the body, okay, you have four types. One is bulk that makes the organ, body, everything. So these are mainly carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Then you will have macro minerals, so like your sodium, potassium, magnesium, calcium, okay, phosphate, okay, sulfate. Okay, these are always present in our blood, or in our body fluids excessively, so that we can maintain our regular activity. Then you have trace elements such as iron, copper, and zinc. And then you have ultra trace elements, okay, like your fluorine, iodine, uh, manganese, cobalt, etc. Now, this is second. Now, if you see all these metals, inevitable, to our body, but at the same time, overdose is lethal. So, if you see the dosage card, so this is the response of your body, then it will have dosage along axis. If you plot it like that, it will come. You will have different regions. So this region we call is optimal. Before that, after a certain region, it is called deficient. Then this region is called survival, because a certain limit, below a certain limit, you cannot survive without that. And if you put extra dose also, that is also not good. This is called toxic, and up to the end, it is called lethal. So to maintain a certain concentration or dose, have to maintain certain dose at any time inside our body, right? So what are the criteria to select these metal ions? Main criteria is first, it should be soluble in our body. Okay, because whatever metal centers or the complexes we will be going to use, that should be soluble in our body fluids. Otherwise, it will not get reacted. Okay, so main thing is the solubility, then stability. As I told you that redox active ions that are not stable against the change in parameters in the body. So that should not be the case. It should be stable. Then coordination atmosphere or environment. Okay. So you see, if some metal ions are inside our body, the protein that will coordinate to the metal, that will also come from inside our body. Okay, like some histidine proteins. Okay, or some DNA base. Okay, it will come and coordinate with the metal. So appropriate coordination environment is required. And then comes kinetic and thermodynamic factors. Some conformation of your metal complex may be stable at some point of condition, but if the condition changes, that it will go back to a other conformation that is thermodynamically stable. So you may have heard about this thing that is called a Chillet effect. Okay, I already discussed, or it is discussed in the course, that when some ligand is there that is forming a ring, suppose this nitrogen 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 nitrogen. Okay, so some ligand is forming a ring, that means it is stabilizing the system. Okay, so for Chillet effect, your entropy decreases, conformational entropy decreases, so it stabilizes. So that is contributing to the thermodynamic factor. Okay, so there are, so these things all have to study from the material or books. So there are some certain proteins and their special tasks, like iron storage protein is called ferritin, and iron transfer protein called transferrin. Okay, so Uh, these two proteins are required to store and store and transport iron ions, okay, in different organs, our muscles mainly, okay, etc. And you have copper proteins also, so that is called plastocyanin for transferring copper ions. So now we'll study some important topic that is called metalloporphyrin. You may have heard about porphyrin a lot because it is present in our body, present inside blood. Hmm. So porphyrin is nothing but a tetrapyrrole ring that is conjugated. So it is like this. So how do you draw a pyrrole ring? So you just first draw like this. Now you connect it with a methylene linker. Okay, the opposite one should be protonated, and now you match the conjugation. Okay, like this. Okay, and then you can have some different R groups here. You have different R groups. Okay, these R groups can be electron withdrawing or can be electron donating also. Okay, so by adding this R group, you can change the ligand field strength. Okay, and as you can see, this whole ring is conjugated. Okay, whole ring is conjugated, and that is why it stabilizes many ions, metal ions. So for our case, iron uh, is of interest. So when iron sits here in this porphyrin, it is connected. So when it connected, then this hydrogen will not be there. So N will connect like this, and this is always Fe2 high spin. Okay, so in our body, it stays like this. Suppose this is iron, and this is your N4 cavity. 4N you have from the porphyrin, all are connected, and one more N is there that is coming from the histidine moiety. Okay, so this is your protein residue, this histidine moiety, and this is connected like this. So one of the coordination is empty. This is empty or vacant. So one thing is there. So this cavity is smaller for iron to high spin system. Okay. So you know why high spin is bigger than low spin because it has electron in the Eg orbital. Eg is anti-bonding. Okay, so that is why its size is bigger. So its size is roughly let me check. Yeah, it is around 0.8 angstrom. Okay, but the cavity is around 0.7 angstrom. So it doesn't fit into the cavity. So maybe this is ring and iron will stay like this. Okay, all the nitrogen will connect it, and here you have N histidine. So it is like that way. But when oxygen comes, so you have two forms of hemoglobin or myoglobin. So you have two forms, deoxy and oxy form. So in deoxy, iron is iron to high spin, and this is 5 coordinated, 5 coordinated. The oxy form, it is iron to low spin. This is 6 coordinated. So when it goes from iron to high spin to iron to low spin, then it strings. Your your size contracts. Okay, radius contracts. So it will be like, so iron will come exactly at the center. You have 4n. These are all connected. So on the top you have oxygen, and down you have histidine. So in this case, Fe2 low spin case, its diameter is around 0.6. So now you can see how much smaller it gets, and so that it fits into the cavity. Okay. Now this is done. Now when oxygen is binding, O2 is binding to myoglobin unit, changing Fe2 high spin to Fe2 low spin. Okay, but then when it is after this one, it gets changed to iron 3 low spin plus sorry, this oxygen will be like this. Okay, this will be single minus. So one electron will be transferred to oxygen, there will be some electron transfer, and then it will go to iron 3 low spin. Okay, that is separate thing. For our case it is not required. So the difference between myoglobin and,
Sir,
yes, yes.
sir, geometry is what if we can geometry
For which one?
high spin?
See, for high spin, your iron is coordinated to 5. Okay, 4 is from the this ring, porphyrin ring, and one is from the another histidine nitrogen. One is empty, right? As I showed it here, this is empty. And as your high spin, your radius is much more, so that is why it cannot stay in this cavity. It has to move out of the cavity. That is why it is little bit down of the cavity, because cavity is zero point 0.7 angstrom, its radius or diameter is zero point 0.8 angstrom. Understand?
Sir.
Hmm. When its radius gets shrink due to change in the spin state, then it contracts. So this zero point 0.6 can be easily accommodated within the cavity. And also with the another vacant site, oxygen is binding. So now it is coordination 6.
Is octahedral geometry.
It's
Okay.
octahedra. Yes, yes, it is
Okay.
octahedra geometry. And the next step will be, when next step will be, so one electron will be transferred from here. Oxygen will be reduced, so it will be O2 minus. Hmm. and this iron will be oxidized to iron 3. Iron 2 will be oxidized to iron 3 plus 10. So the difference between myoglobin and hemoglobin is that basically it is same myoglobin and hemoglobin, but it is a monomer and it is a tetramer. Okay. So for this monomer and tetrameric nature, there is little bit of difference in O2 intake. Okay. So if you see, this curve, so y-axis is the saturation percentage, or represented like this, and this is partial pressure of oxygen PO2. Hmm. Now, as this is percentage, there will be a maximum value. So for percentage, maximum will be 100 always. If you see the curve of myoglobin, it will be like this. Very fast, it will go to the saturation. Very fast is a line for myoglobin. But for hemoglobin, it will not be like this. It will be like this for hemoglobin. But this one, it is dependent on pH. Okay, so this is, I think, at pH 6. Like that, and if you increase the pH, it will behave almost equal to this myoglobin. So maybe I can show it with another color. So this is at pH 8. Okay, is also hemoglobin. Is also hemoglobin. So you can see the difference. Uh, Suppose this value is 5, this value is 13. So 5 and 13, this is the required, threshold partial pressure of oxygen for muscle, and 13 is for threshold for lungs. Because as we are breathing using our lungs, so at lungs our air pressure is much more compared to our other organs, especially muscles, because in muscles we need the oxygen from lungs. This hemoglobin take the oxygen and supply to the muscles. Okay, to do any work, we need this oxygen in our muscles. And when we do the work, when we use this muscle, carbon dioxide is generated, and it gets back to the lung, and we exhale carbon dioxide. This is the general process of oxygen intake and carbon dioxide exhale. So one thing you can see is that how this is dependable on pH. Okay, and why this is not saturating that fast according to myoglobin. So the difference is a basic thing we studied much more earlier, that is called cooperativity in hemoglobin. It is not present in myoglobin because it is a property of a polymer. So did you remember that, as I told you, some different aspect for spin crossover, you can have some gradual and some abrupt switching. You remember, right? So abrupt was for the strong cooperativity in the complexes, polymeric structure. And gradual was for the monomeric system. The same thing is here. Thing is that suppose this is your myoglobin and this is your hemoglobin. All are connected. Okay. So only one unit you have in myoglobin, but hemoglobin you have 4 units similar. So if there is change in one of the porphyrin units, then this signal will get transferred to the other units. and that is why the signal will get transferred to the whole, okay, system, and that is why you can see some of these cooperative effects in these cases. Uh, so something you need to remember, some points you need to remember for metalloporphyrin. So when oxygen is binding, it can get reduced. Okay, as I told you, it will eventually get reduced because some electron transfer will take place from iron 2 to the oxygen to get one one electron reduction. But the concern is that two electron reduction is dangerous. Why? Because form superoxide. No, sorry, superoxide. No, this is called peroxide. Just a second. Forms peroxide. So you all have heard about hydrogen peroxide, right? It is a very reactive chemical. So whenever you are using hydrogen peroxide in the lab, you should be very cautious and careful. So peroxide radicals or peroxide systems are always very dangerous. It is very much reactive. So when oxygen is binding, it is generally recommended to block this two electron reduction. But in our body, so I'll get it later. So normally to block in lab or synthesis in lab, to block this, to prevent the reaction, okay, so you can have different interactions. So this O2 can be weakly bonded to other complex, okay, or uh, if you can give, like, there is no chance, there is no chance of getting electrons from the system. So that way it can be blocked. Like, you are using one metal ion that is not redox active. It cannot give away any electron. Okay, its redox, its potential is very high. Okay, and you are not using any radical kind of ligand or any kind of ligand that will give away electron easily, so to reduce the oxygen. Okay, that is how you can design your ligand. But in our body, what is in our body, so O2 is weakly each bonded to many uh, protein, peptide, parts. Okay, so that it doesn't get some electrons to be reduced. Okay, so these each bonding and short interactions inside our body, these are very helpful. Okay, not only just to block the reduction, uh, to prevent oxodimer formation also. So generally what happens, if you are having this iron 2 oxygen, it will go to iron 3 this kind of dimer it will form. Okay, it will get reduced and then it will form the dimer. So your activity is lost, okay, of the material. So then what you can do to prevent this one, to prevent in synthetic complexes, we use bulk ligand. Bulk ligands is like that. Uh, Bulk ligand is like that. Suppose you have a porphyrin ring, four nitrogens are there, but you have long other appendages. Okay, you have very long R groups. You have lot of phenyl rings. Okay, you have some other appendages extra. So that will block to form this one. Suppose iron is there, oxygen. Then one iron will be here. Okay, but these appendages, due to its steric, it will force not to form the dimer. So this will not happen. So in our body, so this is the synthetic way that is used, but in our body there is already many each bonding interaction that will effectively increase the size of your moiety. Okay, so that prevents your dimer formation with the protein residues stop the dimer formation. Okay, and so this was all about porphyrin. So apart from that, you have hemocyanin also, then hemerythrin. So these are all combining copper, okay, copper 1, copper 2, so like that. And some other enzymes also, such as carbonic anhydrase. So these any study material you can take and you can study these things. So these are mainly informative part, that is consisting zinc. So this helps, carbonic anhydrase helps maintaining pH of our body. This is helping for the carbonate bicarbonate buffer. So maintains buffer in our body. And then you have carboxypeptidase that hydrolyzes certain peptides. You have superoxide dismutase. Okay, etc. So these all things you can study from any material that you can get. So with that, we'll discuss a few of questions today, and then we can stop it for today. So first question is storage of iron in body is carried out by. So four options are there: hemoglobin, ferritin, Cytochrome.
B. B answer.
Huh? Sorry.
B answer.
Yes, yes. So this will be right. As I discussed already, I think in some of the slides it is there. Uh, yes. So you can see iron storage protein is called ferritin and iron transfer is called transferrin. Okay. So storage of iron is ferritin, and this one zero magnetic moment of octahedral, you know, dipotassium nitrogen hexafluoride is due to. So there are four options: low spin D6 Ni4, high spin D6 Ni4, low spin D8 Ni2, high spin D8 Ni2. So can you do it? I'll also try to solve it. Zero magnetic moment. So tier 2 NiF6. So what is the oxidation state of nickel here? Nickel is NiF6 2 minus, that is Ni is 4 plus, right? So Ni4 means D6 system, then it is mu observed is 0. So for D6 we have two configuration. Sorry, this is one can be high spin, one can be low spin. High spin is like this, low spin will look like this. So for which case observed will be 0? Where is no unpaired electron? For low spin case, right? So
Spin, sir.
just match it. So low spin
A. A.
nickel 4 complex, right?
Yes, yes, sir.
This will be right answer. So with that, we'll stop for today. So do you have any question or something? Your exam is when?
Hello. What?
Yeah, your exam is when?
Yeah.
Exam is in March.
Yes, sir. March 22.
Okay, okay. So I think for this course today I'm taking this last class. If you
Yes.
need if you need help with any other question, or if you need to you know want some session for any specific topic, you can ask. Okay, we'll try to get some additional session also.
Okay, sir.
Okay,
Thank you, sir.
if any
Thank you, sir.
study material is required, then also you can ask, not a problem.
Okay, sir. Thank you, sir.
So thank you everyone. We'll meet maybe